click like this. Okay, so let's say that you're a cruel professor, as we all are. Of course, really you're good at heart, but you gotta treat your students a little rough. And let's say homework is coming up, which means for you have a deadline. You got to put some hard problems on the homework as soon as possible. So fine. You're just like, I'll put some random Threeset problems on there, and that'll surely keep them busy. Okay, so what is a Threeset instance? Just to remind you, I'm always going to use I for an instance. I really wish I could click here. Okay, I don't know what's happened, but now we're in good shape. Okay, so a Threeset instance looks like this. There's n variables, x1 through xn. They're supposed to be assigned values 1, 0, and 1. And I'm always going to write delta n for the number of constraints. Okay, so delta is like the density of constraints. And each constraint is, in Threeset, an OR of 3 literals. A literal is a variable or its negation. Okay, so it's going to have delta n constraints. And when I said random Threeset, I wasn't being casual. I'm really going to talk about random Threeset. So this is the case where literally all the constraints are chosen uniformly at random, which variables to apply the OR to, and whether or not to negate them it's all chosen at random. So that's a Threeset instance, I. Okay, now you have to ask yourself, what delta should you choose to really give your students a tough time? Because if you set delta very small, there are very few constraints. There'll be probably any fool could find a satisfying assignment to that. And conversely, if you set delta really high, there's tons and tons of constraints. Any fool can easily recognize that this thing won't be satisfiable. So you have to be careful. So let's put an axis here for delta. And it turns out there's some special magic number for Threeset, 4.2667 are the first few digits, such that when delta is less than this threshold, when you choose I at random in this way, it'll be satisfied with very high probability. And when delta is above this threshold, it'll be unsatisfiable with very high probability. Okay, this actually, I guess technically is not proven, but it's proven for sufficiently large values of 3 by Ding, Sly, and Sun. Anyway, it's true. We won't be very concerned actually about this precise number, just that in some range it's satisfiable and in some range it's unsatisfiable. Okay, so now if you're going to choose delta to be, 4 or something and put that on your homework, tell me about this Threeset instance, then you should write the homework to say, prove that the following instance is satisfiable. Okay, we're actually not going to talk about this regime in this talk because, it's too easy. For example, what is the proof that the students come up with going to look like? It'll just be set x1 to be 0, set x2 to be 1, set x3 to be 0, etc. So it's very easy for them to copy off each other. Also, it's very easy for the TAs to grade it. They just go tick, 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 tick. And as a cruel professor, we want to be cruel both to the students and the TAs. So instead, we're going to talk in this talk about the unsatisfiable regime. So you're going to imagine that maybe you set delta to be 10, you pick a random Threeset instance, and then you put on their homework, prove that the following specific instance is unsatisfiable. Okay, there's a bit of a subtle point here which I want to just emphasize. As I said, I'm not going to be super concerned about this exact threshold. So let's imagine delta is a bit bigger than that, like 10 or something. In that case, the proof of the mathematical theorem that when you do this random Threeset instance with delta at least 10, that with very high probability it'll be unsatisfiable is super duper easy. Anybody can just write it down in 2 lines, use the Chernoff bound, and it's fine. But the thing is, see, once you actually quench that instance, once you actually draw it, and put it down on the piece of paper, prove that this particular instance is unsatisfiable, that could actually be hard. Okay, so the students may well know that you drew this instance uniformly at random with delta equals 10. But once they're actually face-to-face with the instance, it may be hard to actually prove it's unsatisfiable. Okay, the student could write down a whole truth table for all the possible assignments to x and check that none of them work. But that'll take 2 to the n time, and the student doesn't have time for that. Okay. Now, if you're really cruel, Threeset has been worked on a lot, so you might try to go to more general CSPs so they don't get any clues. And what is a general CSP? That stands for constraint satisfaction problem. What does it look like? Sort of similar. So in a general CSP, you have n variables, x1 through xn, and there's supposed to be assigned values in some small domain. So in Threeset, it was 0 and 1, but maybe it could be 0, 1, and 2 or something. And I'm still going to have delta times n constraints. But each constraint is some predicate applied to a small number of variables, okay? And they don't have to have the same arity, but they may as well without loss of generality. Here, all the predicates have arity 5. Okay? And the constraint satisfaction problem itself is sort of defined by what constraints or what predicates you allow. So again, you have some small set of allowable predicates, and each constraint on your piece of paper, PI, should be from that small set. Okay, so for Threeset, you can either think that you have one constraint, which is the OR of 3 variables, but you can also apply it to literals. Or you can think of that as being there 8 different constraints, or with every possible way of negating some of the input variables. Okay, we'll actually probably tend to think about the first one in this talk. Okay, and again, once you fix this, like, let's say, class of allowed constraint types, a random instance is just you choose like everything totally randomly, like which variables to apply it to, which order, which PI comes from the set script P, everything is chosen at random. Okay, so this is a very general class of algorithmic tasks. Of course, the problem again is to decide if there are settings for the variables, an assignment to the variables that make all the constraint predicates true. It's a very general class, and it includes lots of well-known things. So here's one other example besides Threeset. So let's say your domain for your variables is red, green, and blue, and your set of predicates is just the single binary disequality predicate. So like the homework problem looks like this. And I guess you can recognize that this is nothing more than the following situation. This represents a graph, and you're interested in whether or not it's three-colorable. Okay, and in the random model, like all these pairs are chosen uniformly at random. So it's just like a GNP or GNM, I guess, random graph, and you're interested in its three-colorability. Or again, m is fixed to delta times n. Okay, so that's one example. Now, once you get this graph, right, again, to illustrate this point, like you know, if delta is large enough, bigger than 10, it's going to be not three-colorable with very high probability. But when you're faced with the actual graph, you have to figure out how you could actually certify that. So you might like hope that maybe there's like a copy of K4 in there, and then you'd be like, this one is definitely not three-colorable. But that's not going to happen unless delta is like, let's say, at least n to the 1/3, because K4s don't show up in a random graph until the number of edges is like n to the 4/3. Okay, here's another quick example. Back to the Boolean domain, and I'm going to imagine that P is this weirdo predicate called TSA, which has arity 5, and you can apply it to literals. You don't have to like study this example too carefully. This weirdo predicate TSA is like you XOR together the first 3 bits and then XOR it with the AND of the last 2 bits. The exact details are not important, but I bring it up because this particular predicate and random CSPs based on this predicate are quite relevant for cryptography. So in 2000, Ode Golrek had this proposal for like new ways to construct cryptographic objects like pseudorandom generators and one-way functions that would be very efficient. And they're based on the potential hardness of solving random CSPs. And you don't really care what the predicate you use is, as long as it gives you hard problems. So you want these problems to be hard to solve. And you also, for this application, want delta to be large, because delta kind of corresponds to the stretch of the pseudorandom generator that you're potentially constructing. Okay, so all that leads to this following motivation for what problem I want to talk about here, which is this. Let's say you fix some predicate that's going to be your constraints. How large can this cruel professor set delta to be when he's creating random CSP instances with this predicate, such that the students are going to have a hard time? In other words, such that the task of proving that a randomly chosen instance is unsatisfiable will, with high probability, be impossible for any polynomial time student or algorithm, I guess. Okay. So the most familiar CSP is Threeset, so let me tell you what's known for this one. So we're in this regime where delta is big enough that the Threeset instances are going to be unsatisfiable once you choose them at random. Now, once delta is at least n squared, remember the number of constraints is like delta n, so that's n cubed constraints. That's pretty much all the possible constraints. There are only n cubed, basically, choices of 3 variables. So that's going to be like trivially unsatisfiable and trivial to come up with a proof. It's like if you gave someone the complete graph and said, prove that this is not 3-colorable. That's easy. The first interesting result in this area by Beam, Karp, Patasi, and Sachs for 98, it showed an efficient algorithm that could come up with proofs of unsatisfiability with high probability when delta was at least about n, okay, when there are about n squared constraints. Okay, and that was a combinatorial algorithm. And it got really interesting, I think, a few years later with a paper of Friedman and Gert from 2001, where they found an efficient algorithm that can refute or prove unsatisfiability of most Threeset instances as soon as the constraint density is at least n to the 0.5. So that the number of constraints is about n to the 3/2. Okay? I should mention here and throughout the rest of the talk, there's like polylog factors on all these expressions, which I'm not going to mention. Okay, so this algorithm works in a somewhat surprising way. Studies random matrices and eigenvalues and so forth based on the instance. And that's all we know. So like 16 years later, we don't know any efficient algorithms for refuting random instances in this range of deltas. Now, as the cruel professor, you might wonder what the students are going to, what strategy they're going to use. So this algorithm for Threeset is quite specific to Threeset, but actually we now know there's one generic algorithm that will also do the same job. And it's this SOS algorithm, or sum of squares algorithm, that made an appearance in the title of the talk. So let me tell you the story with it. So this SOS algorithm, it's the polynomial time algorithm that all the kids these days are using to solve their problems. Okay, so this is a polynomial time algorithm, and it's super generic. You can use it to try to refute any instance of any CSP. Okay, you just get an instance of a CSP. You can say, I'm going to try to run the SOS algorithm on it to see if it's to try and certify that it's unsatisfiable. In fact, you can use the SOS to try to certify that pretty much any mathematical statement is not true if you want to refute any such statement. But we'll stick to it in the context of CSPs. And the good thing about it is that this SOS algorithm, it kind of encapsulates all known techniques, based on linear programming, semi-definite programming, hierarchies. There's a little asterisk there because some experts may quibble a little with what I'm saying. But basically, any algorithm that runs in polynomial time we also kind of know that this SOS algorithm works equally well. So if you gave me today, if I was solving the homework and you gave me some instance to try to refute, to show unsatisfiable, I would try the SOS algorithm. And then if it didn't work, I'd say, well, I got nothing. Okay. So I'm building up this algorithm a little bit because the result is about proving that this algorithm will fail in certain circumstances. Okay, so this is not the theorem I'm going to talk about today, but it's something I proved a couple years ago with Sarah Allen and David Whitmer. And it's about how well the SOS algorithm works for random instances of constraint satisfaction problems. And it says the following. Let's say you have some general constraint satisfaction problem, P. Let's focus on the specific case where the variables are Boolean, 0 and 1, and you have one predicate P that's applied randomly to literals, variables and their negations. So it tells you a range of deltas where the SOS algorithm will work. Okay, it says this SOS algorithm will work in polynomial time to prove that these instances are unsatisfiable, provided delta is big enough. And how big does delta have to be? It's a certain power of n that depends on the predicate p. So it has this parameter complexity of p, which is some easy to calculate integer. I won't tell you the definition, but you'll eventually get it later. Which somehow measures something about pseudo-randomness related to p. Let me just say that in the case of k-sat, the complexity of this predicate is k. Okay, when p is the OR function of arity k. So in particular, if it's 3-sat, this number up here is 3. So this is n to the 3 minus 2 over 2. That's n to the half, like it was in the earlier algorithm. Okay, so this again is a different way to certify that random 3-sat instances are unsatisfiable once delta is bigger than about n to the 1/2. So SOS will work. So you'd ideally like to have it work when delta is bigger than a constant, but this is the best we can do. So we got to go back to the professor's perspective and try to make things a little harder. So let's imagine that the homework further says, for full credit, I don't want you to just prove that this instance I is unsatisfiable. I want you to actually prove a stronger statement saying that every assignment to the variables x doesn't even satisfy a beta fraction of the constraints. Okay, you should try to do that for beta as small as you can. So it's not just unsatisfiable, it's quite unsatisfiable. So if beta is 1, this yellow command is the same as asking you to prove that the instance is just unsatisfiable. But you might try to prove that no assignment satisfies even 90% of the constraints. That would be a stronger statement. So we would like to do that. And let me tell you about this problem in the context of Threeset. So we have this delta axis, and now we're going to add a beta axis. So here's the truth. This is not hard to prove. So if you pick a random Threeset instance with some density delta, then as soon as delta is bigger than some constant, I don't know, 10 or something, you can easily prove that not only is it unsatisfiable, but every assignment to the variables satisfies at most 7/8 of the constraints. Well, 7/8 plus some little o of 1. Okay, I'm also going to ignore plus or minus little o of 1s in this talk. So it becomes very unsatisfiable. And in case you don't know why 7/8, it's because actually any Threeset instance at all always has an assignment that satisfies at least 7/8 of the constraints. That's by the probabilistic method. If you pick a random assignment, it'll satisfy 7/8 of the constraints in expectation. because the OR predicate is true with probability 7/8 on a random input. So the SOS algorithm is not just good at refuting things. It can actually try to prove stronger statements of this form. And what we actually showed a couple years ago is this, which is even better than what I told you before. So for Threeset, as long as delta, the density, is below n to the 0.5, like SOS can't really do anything. It can't even certify unsatisfiability. But once you get bigger than this n to the 0.5, SOS not only shows with high probability that the random instance is unsatisfiable, it shows that any assignment satisfies at most 7/8 plus some other little o of 1 fraction of constraints. So it really actually certifies the truth about how satisfiable these instances are. OK, so in that paper, we also worked on just arbitrary CSPs, given a predicate P. So in the picture for any CSP, we have the same situation where it's very easy to prove that as soon as the constraint density gets bigger than a constant, the best assignment will only satisfy some constant fraction of the constraints. And that constant fraction is like the expected value of the predicate P, the same probabilistic method argument. And what we proved about the SOS algorithm in this case is kind of crazy. It has a picture that looks like this. So let me try to interpret this for you. So we showed that this SOS algorithm kind of does a better and better job of satisfying like very unsatisfiability as the number of constraints goes up. Okay? So we showed that once the constraint density is a bit bigger than a constant, SOS will certify that a random instance satisfies no more than a sigma 2 of p fraction of constraints. That again is some like easy to compute real number depending on p, and I'll actually define what it is in a second. And then as the number of constraints gets bigger and bigger, SOS doesn't do anything. But as soon as it goes past this threshold n to the 0.5, SOS can suddenly now certify that random instances have the property that any assignment satisfies at most a sigma 3 fraction of constraints. And then once you cross density n, SOS will certify that any assignment satisfies at most a sigma 4 fraction of constraints, and so forth and so on, up to, once you get up to n to the arity of p minus 2 over 2, SOS will certify the truth that like every assignment satisfies at most basically this fraction of constraints.
But those sigmas need not be all different.
Those sigmas need not be all different. They aren't in the case of Threeset. We'll see that in Threeset's case, this equals 1. And they are like actually decreasing like this, but they also don't decrease like at regular intervals or anything. They can basically be any collection of numbers between 1 and this. I'm just cleaning up the picture here. Actually, 1 year later, some people local here, Raghavendra Rao and Shram, showed a stronger statement. If you know about SOS, there's like a parameter to it actually, and you can make it a version of it that doesn't run in polynomial time. It runs in some larger amount of time, but has the potential to be more powerful. So that's this like kind of power versus running time trade-off. And they showed that if you do the version of SOS that takes 2 to the n to the epsilon time for any epsilon, then it gets better. And what effect does it have? It basically has the effect of squeezing the horizontal axis. So like this stair step you can still achieve, but all these n's change to n to the 1 minus epsilons. Okay? So this is everything that we could prove about this powerful SOS algorithm in the context of random CSPs. And the result I'm telling you about today is that everything on this slide is tight. It's completely tight up to like log factors and lower order terms. In other words, SOS does not do any better than this. Okay? You can show that this is the exact true behavior of how well SOS does. And I thought that's kind of surprising because the behavior we proved was kind of this weird stair step. And it shows that this exact three-way trade-off between the constraint density and the quality of the refutation and the running time of SOS, this whole three-way trade-off is tight. OK, so that's a negative result about this particular SOS algorithm. And if you're an optimistic person like me, or you're optimistic about pessimism about hardness, then you might think that maybe this is evidence that like actually no polynomial time algorithm or no algorithm running in more time than you're allotting to SOS can do better than this for refuting random CSP instances. And then maybe therefore this is evidence that the associated cryptographic objects suggested by Goldreich, et cetera, could be secure with these parameter settings. I do want to say some slightly technical things. So let me tell you what this sigma t of p is. Okay, so it's this. So p is some predicate of arity k, let's say operating on k bits. And what is the value? You look at all t-wise uniform distributions on 0, 1 to the k. So these are distributions that for every subset of t of the k positions, xi's marginal is the uniform distribution. And then you just see how much probability mass that xi puts on satisfying assignments for p. Okay, so you try to find the best t-wise uniform distribution in terms of having a lot of probability mass on p satisfying assignments. So let me do an example. In Threeset, p is the OR predicate on 3 inputs. So there are the 7 satisfying assignments for an OR. So let's compute. Sigma 2 of p, here you have to look for a pairwise uniform distribution that has a lot of its probability mass on these strings. And in fact, you can get 100% of the probability mass on these strings. You just let psi be this well-known pairwise uniform distribution that's probability a quarter on these 4 strings, the 4 strings that add up to 1 mod 2. That's a pairwise uniform distribution. It has all of its probability mass on the support of the OR predicate. So sigma 2 of p is 1. On the other hand, sigma 3 of p is 7/8. Because, well, if you look at 3-wise uniform distributions, that just means the uniform distribution. There's no other such distribution. And the uniform distribution puts exactly 7/8 of its probability mass on these 7 strings. Okay? So we computed sigma 2 and sigma 3. So if you go back to this picture, let me interpret it for you a little bit. This means that sigma 2 in the case of Threeset is 1. This gets at what Luca was saying. And indeed, for SOS, like, it doesn't do a good job of anything until delta is like n to the 0.5. And then once delta gets past n to the 0.5, sigma 3 of Threeset is 7/8, which is actually the same as the expectation. So that's the point at which SOS's performance jumps down to being optimal. So this was the picture of how Threeset works with SOS, and like you can infer it from the calculations on the previous slide.
Ryan, what you called complexity before is the smallest t for which sigma t is not 1.
Correct. Okay. Madhur, how much time do I have?
5 minutes.
Oh, great. So these 2 slides are for you, Madhur, because you're the top expert in this room on this topic. So here you go. Okay. So if you know a little bit about SOS, you know in order to show that degree D SOS algorithm fails on some instances, let's just talk about refuting, okay? Fails to refute satisfiability, you need to show that the instance is somehow like degree D pseudo-satisfiable. I'm glad I could work a pseudo adjective into this talk, just as a sop to the title of the conference. So what does that mean? It means that there's a degree D pseudo-distribution on global assignments, or you can also think of it as a signed probability measure on global assignments, and the measure is denoted E-twiddle, such that being a pseudo-distribution, a degree D pseudo-distribution, means you kind of look like an actual probability distribution, like a positive probability distribution. So you need 3 properties that the pseudo-expectation of 1 is 1. And this property encapsulates that like this pseudo-distribution kind of looks like it's assigning all the xi's 0 or 1, in the sense that like xi squared is the same as xi under this pseudo-distribution. And this is the main thing you need, and it's where the degree D thing comes in. This pseudo-distribution or signed measure should have the property that at least it looks positive if you plug in the square of a polynomial. Okay, so if this was a real positive distribution, of course this would always be non-negative. And these pseudo-distributions have the property that at least they're non-negative if p's degree is at most d over 2. Okay, so that's a degree D pseudo-distribution, and you need to show that there is one of these objects that also looks like it's satisfying in fact, that looks like it's a distribution on satisfying assignments for your Threeset instance, even though there are no satisfying assignments for the Threeset instance. So in the case of like, let's say Threeset, you would want, if this was one of the constraints, either x1 or not x3 or x9, you would want that your pseudo-distribution had this polynomial with expectation 0. Okay, so that in particular it means that under this distribution, either x1 is true or x3 is false or x9 is true. So that's your task, to construct this object. And even better, if you get into these things, we actually not only find a pseudo distribution that makes all these things satisfied, we even cook it up so that the pseudo distribution's induced local distribution on any, let's say, 3 variables in a constraint looks like this psi that goes into the definition of like, this sigma t. So this is like the t-wise uniform distribution supported on the predicate. We even want e twiddle to like locally look like that distribution. So it's not only satisfying it, but satisfying it according to this local distribution. Okay, again, so if you're an expert, like you're the T or whoever, they've done stuff like this in the past, and here's the plan always. You define a notion of a closure in a constraint hypergraph, and then you prove that the closures are small in random hypergraphs. And then you define this pseudo-distribution's moments on small sets of variables S based on a planted distribution coming from this psi. And then finally, like the pain and suffering is showing that it satisfies this positive semi-definiteness condition, that it gives a non-negative expectation to all squared polynomials of low degree. So we did all of this, and it was the case that still, like all the main pain and suffering was down here, but actually one thing that I think was nice is in all the previous papers, there was like slightly different definitions of closure. Actually, I think this closure dates back maybe to some work of Sasha's. And I kind of think we found like the right definition of closure. It facilitated us being able to prove this part, and it seemed kind of nice. So that's that. Here's my last slide. So in summary, I think there's something interesting going on in random constraint satisfaction problems with not just satisfiability thresholds, but like algorithmic thresholds as well. So if you take your random CSP instances, we tend to know that there's some satisfiability threshold where if delta is smaller than it, it's satisfiable with high probability. And if it's bigger, it's unsatisfiable with very high probability. And there's been work in, like, especially the statistical physics community about understanding whether or not, and there conjecturally is, a lower threshold for efficient certification. So it seems that there's a lower threshold where in delta down here, there are efficient algorithms for certifying satisfiability, like finding satisfying assignments. And here, it's satisfiable, but it's maybe algorithmically hard to find satisfying assignments. What we kind of saw in this talk, and I think it's a bit interesting, is that there may be sort of a similar threshold above the satisfiability threshold, where if delta is much bigger than this threshold, you can efficiently certify that the instances are unsatisfiable. And maybe below this threshold, they're unsatisfiable, but it's like very hard to prove that. And maybe if you're really speculative, you might think that this threshold is sort of the SOS pseudo-satisfiability threshold. And as for open problems, one that I like is to I ignored kind of constant factors everywhere here. And it'd be interesting to kind of drill down into them, and then you could start talking about this whole picture, maybe of algorithmic thresholds for things like k-colorability and random graphs, which I think is a very nice and natural problem. OK, thank you.
So there seems to be some difference. So you discussed this SOS as solving this problem for other regimes of beta. But it's not the one. When beta is 1, there are some easy predicates which are bad because you can use Gaussian elimination of them.
Yeah.
Do you expect this just to be like a one-off thing, or should there be something qualitatively different between beta equal 1 and beta smaller than 1 for general predicates?
It's definitely qualitatively a difference. I mean, when I said like SOS kind of gives us all the known techniques, it's kind of if you are having epsilons in this beta. So like if you want to not just refute, but like refute that there's an assignment satisfying a 1 minus epsilon fraction of constraints, then I think maybe SOS is the most general thing. But definitely there is something different about beta equals 1, Gaussian elimination, and well, of course, the whole dichotomy conjecture is a totally different realm of things. So I'm not sure SOS is relevant for that. Yeah.
You did not say anything about the degrees of source programs your results applied, so constant or?
Yeah, so our results actually gave a trade-off for every value of the degree. So I kind of implicitly equated it with the running time. So the running time for degree d is like n to the d. So when I was talking about Raghavendra Rao and Schramm's results for running time 2 to the n to the epsilon, that really meant degree n to the epsilon. And epsilon was a free parameter there.
So what's, when the degree is any fixed constant, then your lower bound applies, right?
Our lower bound applies for every degree, even a function of n. So we have the tight, complete trade-off in terms of the SOS degree, the quality of the SOS refutation, and the constraint density. Any more questions? Okay, thank you.